Welcome to A-Level and AP Physics. Today we will start a new series of videos for A2 Physics. In this series we will discuss all typical graphs, or simply we can say all possible graphs for A2 Physics, and we will discuss these graphs topic wise, so you can improve your conceptual understanding of each topic, and also you can have better understanding of this type of questions. Most of the time students, they struggle with graph questions. Simply they cannot understand how to answer them. And if you watch this series of videos carefully, I'm quite confident you will improve your conceptual understanding and you will be able to handle graph questions with confidence. It will also help you to improve your score in your exams, means you can get better scores in your coming exam. So watch them carefully, and if you have any questions about these graphs, you can leave your questions in comments and I will answer as soon as possible. Let's study together, let's improve together. Question says electromagnetic radiation of wavelength lambda is incident on a metal surface. Electrons of maximum kinetic energy Emax are emitted. On figure 11.1, sketch the variation with 1 over lambda of Emax. So simply we need to sketch the graph between Emax and 1 over lambda. So for this question, now the question is that where to start. So you need to find the relationship between Emax, means kinetic energy maximum, and 1 over lambda. So for this purpose you have to use Einstein's photoelectric effect equation, and this equation is the fundamental equation for this whole chapter, so it's very important one. So you need to understand the energy of coming photon. This will be distributed between kinetic energy max. I can simply write on Emax. So this is the kinetic energy max of photoelectrons. So this one is the kinetic energy max of photoelectrons, means the electrons emitted due to photoelectric effect, plus work function of metal. So this is work function of metal. It depends on metal. If the metal change, work function will change. Now simply we need to rearrange this one. So this is K Emax, so don't get confused with this one. This is kinetic energy maximum. So if we rearrange this one, we can say K Emax. In this case, this is equal to energy of photon, and energy of photon I'll be writing here. Energy of photon, we can say this is equal to H times F, or simply we can say this is equal to Hc over lambda. So we can write down here Hc over lambda minus we have work function of metal. We can further rearrange this one. We can say this is Ke max. This is equal to Hc times 1 over lambda minus we have this is work function. Now simply we can compare this one with straight line equation. We can write on y, this is equal to mx plus c. From here we can see c is equal to negative work function, and gradient in this case is equal to Hc, and this is positive, so it means it's a straight line with positive gradient. So straight line with positive gradient, because this is 1 over lambda. So K Emax and 1 over lambda, the graph between these two quantities, it has to be a straight line with negative y-intercept. So simply we have to draw the line here with y-intercept. So it has y-intercept, so you cannot draw from here. This one will be wrong. It means it has no y-intercept. It has y-intercept, so it should start from here somewhere. A number is not required, so you can start from anywhere, but you cannot start from the origin. Now if we extend this one, so this is our y-intercept, so you will get value of phi, the value of work function you will get from y-axis. So value of work function you will get from here. So this is value of work function. So this is how you need to sketch. So this is how you can sketch this one. Let me clean. So this is how you need to sketch for the answer of this question. Now if we go to the second part is asking us state an equation relating the gradient of the graph drawn on figure 11.1 to the Planck constant h. Gradient of the graph drawn on figure 11.1 to the Planck constant h means how gradient and Planck constant, they are linked together, relating these two, gradient and Planck's constant. So gradient, we have already discussed that gradient is equal to h times c. Gradient is equal to h times c. Explain any symbols you use. So in this case, the symbol we have used this symbol. So this is the symbol we have used. So for the answer of this question, simply you will write down gradient. You will say gradient first of all, because you have to write down state and equation. So you have to write down this is equal to hc. Then you will say c is speed of light. So these 2 points you have to write down. You will say c speed of light, because this is the symbol we are using other than stated symbols in the question. So this is speed of light. So simply you need to write down this is speed of light. So if you write down this one, you will get 1 mark for this part, and you will get 2 marks for this part. I hope this one is clear to you. Part C says the metal surface in B becomes oxidized. Photoelectric emission is still observed, but the work function energy is increased. On figure 10.1, draw a line to show the variation with 1/lambda of Emax for the oxidized surface. If you look at figure 10.1, we have Emax on y-axis and we have 1/lambda on x-axis. So this graph will be very similar to the previous one. So first of all, we can write down Einstein's photoelectric effect equation. Means Emax, this is equal to energy of incident photon minus work function. We can little bit rearrange this. We can say Emax, this is equal to hc times 1/lambda minus we have work function. And now we can compare this one with straight line equation. Y is equal to mx plus c. So in this case we have the gradient. So this is the gradient and this is positive. And y-intercept, this is equal to minus 5. So the graph has to be a straight line. But the question is that it is given to us that work function has been increased in this case. So work function, this is equal to negative 5. If this one has increased, it means that the c has to be greater. C has to be greater. So simply you need to understand this point. And gradient is the same, because still gradient is equal to hc. H is constant, c is constant. So these two lines, they must have the same gradient. In order to sketch this one, first of all, we can extend this line. So we can extend this line. We can simply extend this one. So this line we can extend. Now we need to draw a line that y-intercept is greater. So we have 2 options. You can draw the line here, but if you draw the line here, you can compare these 2 work functions. So we can make it little bit parallel. So these 2 lines have to be parallel. Now if I extend this line, for example, from here, you will see the previous line. We can say this is line, let's say this is line 2 and this is line 1. So in this case you can see phi 1, this one is greater than phi 2, mean the c1, we can also say c1 is greater than c2. It means this is not right line, so this is not possible. So we can draw below this one. So you can check this one just for your better understanding. I want you to check this. So if I draw the line under this one, let me clean this part and draw a line under this. So this one I can draw third line here. You can see this third line, its y-intercept is greater, so it means that we have to draw the line below the given line. So line has to be below this one, because in this case if I say this is third line, this one is third line, so you will see the work function of third one, this is greater than work function of the first one. So this is the right one and this is incorrect. So simply you need to draw a line below the previous given line, and it has to be parallel and it has to be below. So this is how you can draw. So this is what you need to draw for the answer of this question. Rest of the things you need to understand why we draw a line like this. So this line you have to draw and it has to be under the previous line. Part B says photons having wavelength lambda are incident on a metal surface. The maximum wavelength for which there is emission of electrons is lambda naught. For photons of wavelength lambda naught by 2, the maximum kinetic energy of emitted electrons is E max. Maximum kinetic energy of electrons is E max when wavelength of incident photon is equal to this. On figure 5.2, sketch the variation with wavelength lambda of the maximum kinetic energy for values of wavelength between lambda is equal to lambda naught by 3 and lambda is equal to lambda naught. Mean between these points, between this point and this point. For this question we have E max on y-axis, so this is E max. Again, kinetic energy maximum we have on y-axis, but on x-axis we have lambda instead of 1 over lambda. So the shape of the graph in this case, it will not be a straight line. So we can start again with photoelectric effect equation. We can write down E max. This is equal to Hc over lambda. This is wavelength of incident photon minus we have work function. But we need to understand work function. This is equal to Hc over lambda naught, and lambda naught actually this is the threshold wavelength, so we call this is threshold wavelength. So we can write down this is threshold wavelength. So this is maximum value of wavelength. If we increase more wavelength than that, there will be no emission of electrons, so we call this is threshold wavelength. Now simply we can write down in this case E max, this is equal to Hc over lambda. First of all, we can start when lambda is equal to lambda naught. So we can write down here lambda is equal to lambda naught minus work function we have. This is also Hc over lambda naught. So in this case, E max will be equal to 0. So this is one thing we can write down. E max in this case will be equal to 0. So this is one point we can write down. So E max has to be equal to 0. Now in the question it is given to us when lambda is equal to lambda naught by 2, kinetic energy, maximum kinetic energy of emitted electrons, this is equal to E max. So we can rewrite here. So I'll be writing here. So we have E max. So this is the second case, E max. So this one is the first case when lambda is equal to lambda naught. We can say this one is first case. Now we are looking at the second one. E max, we can say this is equal to Hc over lambda. So we have lambda. Now we need to replace this lambda with lambda naught by 2. So we can write on this is lambda naught by 2 minus we have this Hc over lambda. Now if we rearrange, we can say this is 2Hc over lambda naught minus we have this Hc over lambda naught. So we will get here this is equal to Hc over lambda naught, and this is given to us, this is equal to E max. So this is equal to E max. So this is the second one. So when lambda is equal to lambda naught by 2 means then the wavelength of coming photon is equal to lambda naught by 2, kinetic energy, maximum kinetic energy of emitted photoelectron, this is equal to E max. So this is the second point. Now we need to understand when lambda is equal to lambda naught by 3. this one. Now simply again we can replace this lambda with lambda naught by theory. So we can use different color. So we can say in this case Emax, this is equal to HC. Lambda we need to replace with lambda naught by theory. So this is lambda naught by theory minus we have HC over lambda naught. Now if we rearrange this one, we can write down this is HC over lambda naught, and we have theory here minus this is HC over lambda naught. So we will get here in this case this is equal to 2HC over lambda naught. But we need to understand that Emax is equal to HC over lambda naught. So it means this is equal to Emax. So simply we can say here we have 2 times of Emax. So this one you can also say this is Emax 3, this one you can say Emax 1, and this one we can say this is Emax 2. And Emax 2 is equal to Emax. So this is Emax. This is equal to HC over lambda naught. Emax. This is given in the question. This one is already given in the question. When wavelength is equal to this one, Emax is equal to this. So this is equal to 2 Emax. So from here it is 2 Emax here, this point. So we can mark this point. And now we need to connect this point by a curve. So we can connect these points. So it will be connect points like this. So we can draw this one a bit better. So simply you need to connect these points now. So this one looks better. So this is how you need to sketch the curve. So let me show you the better one. You can sketch like this. Yes. So this is how you need to sketch. This question is a beautiful question. You need to understand if the graph between Emax and lambda, the shape of the graph has to be like this, and hyperbola, so shape has to be like this, and it has to be a curve, and when lambda is equal to lambda naught, it has to be 0. Emax has to be 0. So this point you have to keep in your mind. I hope this one is clear to you. If you have any questions about this one, leave your questions in comments. But this is a beautiful question. Practice by yourself more than 1 time, and you will be very confident about quantum physics graphs. Question 10 part A says a metal surface is illuminated with light of a single wavelength lambda. On figure 10.1, sketch the variation with lambda of the maximum kinetic energy Emax of the electrons emitted from the surface. On your graph, mark with the symbol lambda naught the threshold wavelength. So if you look at this figure, on y-axis we have Emax, and on x-axis we have lambda wavelength. And the same type of graph we have just sketched in the previous question. It means shape of the graph has to be the same. So again we can start with Einstein's photoelectric effect equation. Most of the graphs you will see are just based on Einstein's photoelectric effect equation. So again we can start with Emax. So the Emax, this is equal to HC over lambda, this is wavelength of incident photon, minus work function SC over lambda naught. From here we can take HC common. So we have here 1 over lambda minus we have 1 over lambda naught. So first of all, in this case we can look at first case when lambda is equal to lambda naught. So in this case we will have HC and 1 over lambda naught. So we will have here 1 over lambda naught minus 1 over lambda naught. So this one will be equal to 0. It means Emax will be equal to 0. So we can simply mark here any point somewhere here we can mark, or you can mark here anywhere, it doesn't matter. So let's say this is value of lambda, that is equal to lambda naught. So Emax at this point has to be 0. Now we can look at the second case. We can say this is over case 1. Second case we can say we have Emax that is equal to HC, and this is 1 over lambda minus 1 over lambda naught. Now we can consider the extreme case when lambda is equal to 0. When lambda is equal to 0. If lambda is equal to 0, so we are assuming lambda is equal to 0, so E max in this case you will see this will be equal to HC times 1 over 0, means infinite, minus 1 over lambda naught. So what we will get in this case, we will get this will be infinite, mean E max will be infinite. So E max will be equal to infinite. So this is extreme case. Physically this is not possible, but for the sake of understanding of this question, mathematically we can assume when lambda is equal to 0, it means it will never reach maximum value until infinity. So there will be along y-axis, there will be asymptote along y-axis, and the graph will intersect x-axis at this point. So simply we can draw the curve. So it has to be a curve and it has to cross this one. So it has to cross somewhere here. So this is how you need to sketch. So I hope this one is clear to you. Similar shape as we have done in the last part. So we have looked at two cases. One case when lambda is equal to lambda naught, so it has to be E max has to be 0. The second case, if lambda is 0, but physically that is not possible, but theoretically we can assume. So E max has to be infinity. There will be asymptote along y-axis. So this will be the shape of the graph, hyperbola. These two quantities, they are inversely proportional. So when lambda is decreasing, E max is increasing. Part B says a neutron is moving in a straight line with momentum p. The de Broglie wavelength associated with this neutron is lambda. On figure 10.2, sketch the variation with momentum p of the de Broglie wavelength. Mean how de Broglie wavelength is changing with momentum. For this question, we have lambda on y-axis and we have momentum of neutron on x-axis. According to de Broglie wavelength lambda, this is equal to h over p, and this quantity is constant. So it simply means that when momentum increase, wavelength of neutron decreases, and vice versa is also true. So simply we can say in this case lambda times p, this is equal to constant, Planck's constant, and this is a constant quantity. So the relationship between these two quantities is inverse relationship, or simply we can say they are inversely proportional. So the shape of the graph has to be rectangular hyperbola, inversely proportional. So simply this is how you can sketch the graph. The shape of the graph has to be somewhat like this. So this is how you can sketch the graph. Let me show you the better shape of the graph. So if you draw in a better way, in a proper way, the shape of the graph will be like this. And that's all for today's lesson. And in the next lesson, we will talk about one new topic. May we discuss about nuclear physics and AC in the next video. Welcome to A-Level and AP Physics. In today's lesson, we will try to discuss all possible graph questions from nuclear physics. In the last video, we have already discussed all possible graphs from quantum physics. And we will discuss these questions in detail so you can improve your conceptual understanding of this topic, and also you can have better understanding of graph related questions. Let's study together. Let's improve together. Question 9 part A says an isotope of an element is radioactive. Explain what is meant by radioactive decay. Radioactive decay is simply a name of process in which an unstable nucleus emits alpha, beta or gamma radiations to become a stable nucleus. And it emits alpha, beta and gamma radiations randomly and spontaneously, and this process we call is radioactive decay. Let's try to understand this one in a proper way. Imagine that we have unstable nucleus. So simply we can write on, we have unstable nucleus. This nucleus can become stable nucleus, by emitting alpha particles or by emitting beta particles or by emitting gamma radiations spontaneously and randomly. So we will call this process radioactive decay. So let me show you the answer, how you can write down your answer. So this is how you can write down your answer. In your answer you can say, during radioactive decay, the unstable nuclei release alpha particles, beta particles or gamma ray randomly and spontaneously to become more stable nuclei. So randomly and spontaneously are very important because radioactive decays are random in nature and also spontaneous in nature. So you have to mention this one in your answer, then you can get 3 marks for this question. Part B says, at time t, a sample of radioactive isotope contains capital N nuclei. In a short time delta t, the number of nuclei that decay is delta n. State expressions in terms of symbols t, delta t, capital N, and delta n for the number of undecayed nuclei at time t plus delta t. So for this question, it is given to us at time t, we have number of nuclei that is equal to n. So we can say number of nuclei. So we have number of nuclei that is equal to capital N. Question is, and it is also given to us that in time delta t, the number of nuclei decayed. So we can say decayed nuclei in delta t, decayed nuclei in time delta t. So how many have been decayed? That is equal to delta n. Now question is asking us, at time t plus delta t, undecayed nuclei. At t plus delta t, we need to write down undecayed nuclei. We need to find out undecayed nuclei. So this is simply n minus delta n. So we have n minus delta n because delta n has been decayed and initially we have n, so n minus delta n. This is number of undecayed nuclei. So simply we can say n minus delta n. For the second part, question is asking us to write down the mean activity of the sample during the time delta t. Activity is the number of nuclei decayed per unit time. So activity, we can say this is equal to decayed nuclei. So simply we can say this is equal to decayed nuclei. So this is equal to decayed nuclei over time taken. So decayed nuclei we have that is equal to delta n. So activity is simply equal to delta n divided by time taken, that is delta t. So we can write down this. Next one is the probability of decay of a nucleus during the time interval delta t. And probability, this is equal to success over sample. Success means the number of nuclei decayed. In this case, number of nuclei decayed, we have delta n. Delta n has been decayed, and the initial number of nuclei in the sample initially we have capital N. So this one is the probability of decay of a nucleus. Next one is decay constant. Decay constant, we use symbol for this one, lambda. This is probability of decaying per unit time. So this is the probability of decaying of a particular nucleus, of decaying of a particular nucleus per unit time, or in any given time, per unit time. Probability of decaying of a nucleus per unit time, probability of decaying. So we already have the probability, we have calculated. This is delta n by n. So this is the probability, and this one has to be divided by delta t in given time. So simply we can say this is equal to delta n by n multiplied by 1 over delta t. So this is how we can write down decay constant. Part C says the variation with time t of the activity capital A of a sample of a radioactive isotope is shown in figure 9.1. If you look at figure 9.1, we have activity on y-axis and we have time on x-axis. And if you look at this one carefully, we can see after one half-life, activity becomes half, means activity here, this is equal to A by 2. And after another half-life, activity again becomes half of the previous activity. So this activity will be equal to A by 4, means half of this one. We can also say this one is the initial activity. We can say this is A0, and after one half-life we have activity A1. After another half-life we have this is activity A2, and after another half-life we have activity A3. This will be half of this, so this will be simply equal to A by 8. So this is how activity is decreasing. But for this question, we have to sketch a graph between N and T. If you read this question, it is given to us the radioactive isotope decays to form a stable isotope capital S. At time t is equal to 0, there are no nuclei of S in the sample. On the axis of figure 9.2, sketch a graph to show the variation with time t of the number n of nuclei of S in the sample. So we need to sketch a graph to show how number of nuclei of S increase with time. In order to understand the relationship between A and N is the number of nuclei. So simply we need to understand that A is equal to lambda times N. N is representing number of nuclei of daughter nucleus, of daughter product. So from here we can say A is directly proportional to N. So it simply means that when A is half, N is also half, and vice versa is also true, and so on we can simply say. So when this is A by 4, this is 1/4, this also has to be 1/4. Now let's try to understand how parent nuclei and daughter nuclei, they are linked with each other. Imagine that we have X isotope. It has 100 nuclei. After one half-life, so we can say after one half-life T 1/2, they become half. So simply we will have 50 nuclei of X and we will have 50 nuclei of S. And after another half-life, this 50 again divided into 2. So first of all we have here, so we have this is 25. Now 50 become half, we have 25x, so this become 25s, and this one we have 50s. So now we have 75 and so on. And if you write on one more step, means after another half-life, so we can say here after another half-life. So now in this case this 25 will be divided again by 2, so we will have here 12.5 nuclei of X, and rest of them they will be X, so this will be X. So we will have about 87.5 S. So these nuclei S. Let's try to understand a little bit more about S, how number of S nuclei are increasing with time. So here if you look at number of nuclei of S, we have 0 nuclei, and after one half-life we have 50 nuclei of S. So we can say S is equal to 50. And after two half-lives we have number of nuclei of S, that is equal to 75. And after three half-lives we have number of nuclei of S, that is equal to 87.5. We can say this is S0, the initial number of nuclei, and this is after one half-life, this is after two half-lives, and this is after three half-lives. But the proper way to represent this one is we can express this one in terms of percentage. So initially we have 0%, then we have 50%, then we have 75%, then we have 87.5% after 3 half-lives. So we can also label here. So we have 25% on this axis. Here we will have 50%. Here we will have 75%, and here we will have 100% number of nuclei in the sample. So first of all, we have 0, so we can use one dot here. After 1 half-life we have 50%, after 2 half-life we have 75%, and after 3 half-lives we have 87.5%. Now simply we have to connect these points. So we can draw this exponential growth curve like this. So this is how you need to sketch the graph. I hope this one is clear to you. Let me show you a better one. Let me show you the better one, a proper graph. So this is how you can sketch a proper one. So let me clean this part here with percentage, you can see. So this is how you need to sketch the graph. For the sake of this question, simply what you need to do is you need to simply sketch this graph. Rest of the things are for your understanding. Why do we sketch like this? I hope this one is clear to you. Question 2, part C says a pure sample of radioactive isotope contains N0 nuclei. The half-life of the isotope is T sub half. The product of the radioactive decay is stable. The variation with time T of the number N of nuclei of the radioactive isotope is shown in figure 5.3. So this is for radioactive isotope, this curve. On figure 5.3, label on the time axis the time T is equal to 1.0 half-life and T is equal to 2 half-lives. Sketch the variation with time T of the number of nuclei of the decay product for time T is equal to 0 to T is equal to capital T, means until this time. So we need to sketch for decay product. Now the same concept. So if you look at this radioactive isotope, we can see N becomes half. N becomes half after 1 half-life. So first of all, we can label here. Here is 1 half-life. So this is 1 half-life. So here we have 2 half-lives. So this time will be equal to 2 half-lives. And this time, this will be equal to 3 half-lives. So this is first of all how we can label. Now, when radioactive isotope, number of nuclei of radioactive isotopes become half, number of nuclei of decay product also become half, means become 50%. So here become 50%. And now here we have 25% of nuclei of radioactive isotope. So we will have 75 of decay product, and again it become half, so it will be halfway here. So 1 2 3 4 5. So simply 1 2, so we have 1 2 3 4 5 here. Now simply we need to connect these dots and curve for the decay product. That will be just reflection of this curve, just reflection. So let me connect these dots. So if we connect them like this, so this is just reflection. Now let me show you the better one, how you can sketch a better one. So this is how you can sketch a better one. This is what you need to sketch in your exam. So we can clean the previous one. So this is how you can sketch just reflection. And this graph is a typical graph. You will see in lot of past papers, always they're asking you about this exponential growth graph. And so this is how you need to sketch. So let me highlight one point. This is for radioactive isotope. So this is for radioactive isotope. Just label this one. And this is for decay product. Decay product. Decay product is stable. This one is stable, but this one is unstable. unstable. So this is all what you need to do for this question. Question 13 part A says explain what is meant by gamma radiation. Gamma radiation is simply electromagnetic wave emitted by decaying nuclei. When unstable nuclei become stable nuclei, they emit alpha, beta and gamma radiations. And gamma radiation is one type of nuclear radiation that is emitted during radioactive decay. Now let me show you how you can write down your answer. For the sake of answer of this question, simply you can write down is an electromagnetic wave. If you mention this one, you will get 1 mark, and then if you have mentioned it is emitted from a decaying nuclei, you will get another mark. So you will get 2 marks for this question. Question B says a source of gamma radiation is placed a fixed distance away from a detector and counter as illustrated in figure 13.1. A sheet of lead of thickness X is placed between the source and the detector. The average count rate capital C corrected for background is recorded. This is repeated for different values of X. The variation with thickness X of ln C is shown in figure 13.2. Here we have figure 13.2. So this is figure 13.2. If you look at this figure carefully, on y-axis we have ln of capital C, means ln of average count rate, and on x-axis we have value of thickness. This is given in millimeters. In the next part, actually we need to calculate the gradient of the graph. So first of all, we will draw a best fit line. So this is how you can draw the best fit line. So you can see in this best fit line we have the same number of dots. We have 1 dot, this is below this best fit line, and this 1 dot is above this best fit line, and the distance from the line is almost same. And if you look at this point, this is below this best fit line, and its distance from the line and the distance of this point from the best fit line is also the same. It means this line fit all the points. So this is our best fit line. Now we will go to the next part and we will try to answer the next question. If you look at this question, for this question it is given to us that the absorption of gamma radiation in lead may be represented by this equation, where C0 is the count rate for X is equal to 0 and mu is the linear attenuation coefficient. Use figure 13.2 to determine the linear attenuation coefficient mu for this gamma radiation in lead. So we have to determine the value of mu. Mu is given here, so here is mu. But if you look at this figure, we have ln of C on y-axis. So it means we have to take ln on both sides. So we will write on C is equal to C0 e to the power of negative mu x. So this is typical exponential curve, equation for exponential curve. Now if we take ln on both sides, we can say this is ln of C. This one will be equal to ln of C0 minus we have mu x ln of E. But ln of E, this is equal to 1. Ln of E, this is equal to 1. So simply we can write down, we have ln of C, this is equal to negative mu x plus we have ln of C0. Now we can compare this one with straight line equation. Y is equal to mx plus C. So in this case, gradient is equal to negative mu. And y-intercept is equal to ln C, means you can find the value of ln C0 from here. So we can say in this case, gradient, this is equal to negative mu. So this is equal to negative mu. First of all, we can say this is equal to negative mu, and we can say mu is equal to negative of gradient. So this is the point you need to understand. We will calculate the gradient and then we will take negative of gradient, that is value of mu. So mu will be positive in this case. So now simply we can take 2 points on this one. We can take 1 point here, so we will be taking 1 point here and we will be taking another point here. So we have taken these 2 points. Maybe these 2 points are very small to see, but I'll be writing the coordinates here. So we have coordinates of this one, that is 2.4 comma we have 3.75, and coordinates of these points we have, this is 14.4 comma we have 3, this is here. Now we need to calculate the gradient of this one, so we can calculate gradient. So we have this point. First of all, we have 3 minus 3.75, and this is divided by 14.4 minus we have 2.4. If we solve this one, we will get negative 0.0625 up to 2SF. We can write down this is 0.063. So this is the gradient and this is negative, so gradient is equal to this one, so we can say gradient. So the mu in this case, mu will be equal to 0.063 per millimeter, because log of any quantity, it has no unit. Log of any quantity, it has no unit. So the answer for this one is 0.063 per millimeter. So this is the answer. In the mark scheme, given answer for mu is 0.061 per millimeter plus minus 0.004, and our answer is in this range. So this is how you can figure out value of mu. Part C says the value of mu calculated in B is for gamma radiations in lead. Suggest and explain whether the value of mu for aluminium would be the same, greater or smaller. Suggest and explain. So we need to understand, if we pass gamma radiations through lead and we pass gamma radiations through aluminium, in which metal gamma radiations are more absorbed? So simply I hope you will say gamma radiations are easily absorbed by lead, means lead will absorb more gamma radiations, and aluminium, it will absorb less. So we can say aluminium. So here we have aluminium and here we have lead. Aluminium absorb less, it will absorb less, and this absorb more. So we can say absorb more. If it absorb more, it means mu will be greater for this one and mu for this one will be less. So we will simply say mu for aluminium, it has to be smaller as compared with mu for lead, means for PB. So if mu is smaller, it means the gradient. So we can say the gradient. So gradient for aluminium also has to be shallower as compared with gradient for lead. So that's all what you need to understand. Lead is very good at absorbing gamma radiations, but aluminium is less absorbing. So the value of mu for aluminium will be smaller, and mu is equal to negative of gradient. So the gradient of the graph also will be smaller. So if these points are clear to you, now let me show you how you can write down your answer. In your answer, you have to mention these points. Aluminium is less absorbing compared to lead. Gradient of the graph will be smaller, hence a smaller value of mu. Part C says a radioactive isotope decays with a half-life of 15 seconds to form a stable product. A fresh sample of the radioactive isotope with time t is equal to 0 contains n naught nuclei and no nuclei of the stable product. On figure 6.3, sketch the variation with time t of the number n of nuclei of the stable product for time t is equal to 0 to t is equal to 45 seconds. Half-life is given to us, half-life of radioactive isotope, that is equal to 15 seconds, and we need to sketch from t is equal to 0 to t is equal to 45 seconds. It means we have 3 half-lives. So we are talking about stable product in this case. Stable. We are talking about stable product. Stable product, initially it has no number of nuclei, so initially it has n that is equal to 0, and after one half-life n will increase to 0.5 n naught after one half-life, and after another half-life this will be equal to 0.75 n naught, and after another half-life this one will be equal to 0.875 n naught. So this is after one half-life, t1 by 2, and this is after 2 t1 by 2, and this is after 3 half-lives. So this is after 15 seconds, this one will be after 30 seconds, and this will be after 40 seconds. Now simply we need to label these points. So first of all we have 0.5, so after one half-life we will have 0.5, and after 2 half-lives we will have 0.75, and after 3 half-lives we will have 0.875. so 1 2 3 4 5 means half of that every time. So half of this one, half of this. Now simply we need to sketch this one, so we need to connect these dots. So this is growth graph, so exponential growth graph, the shape will look like this. So this is how you need to sketch. It's a typical type of question, so you need to read question carefully. You need to sketch graph for the stable product, or you need to sketch graph for radioactive isotope. So this is for stable, so it means this is growth graph. So this has to be growth graph. So this point you need to understand. If question asks you to sketch for radioactive isotope, it has to be decay graph. So it has to be decay graph. Decay. This is decay, this one is growth. Let me show you the proper graph how you need to sketch. So this is how you need to sketch a proper one. Let me clean this. So this is how you need to sketch. If you wanna label this, we can also label. This will be 0.75 and this will be 0.875. And that's all for nuclear physics. I hope you have better understanding of nuclear physics. And for quantum physics, you can check part 1. In part 1 we have already discussed about graphs for quantum physics, and you can find all the possible graphs for quantum physics in part 1. Welcome to A-Level and AP Physics. In today's lesson, we will discuss all possible graph questions from electromagnetic induction topic. In this lesson, we will discuss all questions in detail so you can improve your conceptual understanding of EM induction, and also you can have better understanding of graph questions from this topic. Let's study together. Let's improve together. Question 10 says two coils P and Q are placed close to one another as shown in figure 10.1. For part A, it is given to us the current in coil P is constant. An iron rod is inserted into coil P. Explain why during the time that the rod is moving, there is reading on the voltmeter connected to coil Q. So first of all, we have coil Q here, and next to this one we have coil P. In the question it is given to us an iron rod is inserted into coil P. So this one is the iron rod. We need to understand iron is a magnetic material. It's a soft magnetic material. And when magnetic material is placed inside an external magnetic field, it also becomes magnet. So it simply means that when we insert iron rod into coil P, magnetic field increases. We can say magnetic field increases. So magnetic field increase. As magnetic field will increase, and magnetic field here also will increase. Magnetic field here will also increase. So simply we can say there is change in magnetic flux. Change in phi means change in magnetic flux. So here is change in magnetic flux, because here is change in magnetic flux and here also will be change in magnetic flux. As there is a change in magnetic flux, and inside changing magnetic flux we have an iron core. Change in magnetic flux, and as there is a change in magnetic flux here, and inside changing magnetic field we have copper coil. Change in magnetic flux. So copper coil, or simply we can say coil Q inside changing flux. So we can say simply inside changing flux. So there will be EMF, induced EMF. So we will say there will be induced EMF in Q. So we can say induced EMF in Q. So EMF will induced in Q. So these are the points you need to understand. First of all, when iron core is inserted, we're inserting this one inside. Magnetic field inside coil P is keep on increasing as long as the iron rod is moving. So there will be change in magnetic flux in coil P, and also there will be change in magnetic flux in coil Q. As coil Q is placed inside changing magnetic flux, so there will be EMF induced in coil Q. So these are the points you need to write down for the answer of this question. This question has 2 marks. Now let me show you the answer, how you can write down your answer in the proper way. So this is how you can write down your answer. Simply these points are important. You need to write down magnetic field around coil P increases. This changing magnetic flux is cut by coil Q. This is cut by coil Q, therefore inducing an EMF in coil Q. So these points you have to mention in your answer, and this is a typical type of question, so you need to clear your concept about this one. If once your concept is clear why magnetic field is increasing, then many questions about this topic you can answer. For part B, it is given to us the current in coil P is now varied as shown in figure 10.2. On figure 10.3, show the variation with time of the reading of the voltmeter connected to coil Q for time t is equal to 0 to time t is equal to t2. Current in coil P is given to us, and it is given to us how current in coil P is changing with time, and we need to sketch the graph for EMF induced in coil Q. And so for this purpose, simply we need to understand how EMF changes with current. So simply we can say EMF, this is equal to d phi by dt, and EMF we can also say this is the gradient. So it simply means that when I write down EMF is equal to d phi by dt, it simply means that I'm talking about gradient of flux against time graph, means the gradient of this graph, this is equal to EMF. We can also say that as flux is directly proportional, so we can write down flux as flux is directly proportional to B, so we can also say that gradient of we can say gradient of BT graph, that is also representing EMF, or we can say proportional to EMF. For solenoid means for coil B is equal to mu naught Ni. So from here we can say B is also directly proportional to I. So the gradient of IT graph, so gradient of IT graph also represents EMF. But for EMF you need to understand we have a negative sign here due to Lenz's law. We have negative sign here, so it means negative gradient of this graph, and negative gradient of IT graph, that is representing EMF. So this is very important point. This has to be in your mind, and you will see most of the graph about electromagnetic induction, they are simply based on this concept. Now we have in this case I against T graph, so we can say EMF, this is proportional to minus di by dt, or simply we can say this is negative gradient of IT graph. So we can write down IT graph. So this is the main concept you need to understand to answer this question. So if you look at this gradient of this part until this point, gradient is positive, so EMF induced, it has to be negative. So we can draw, for that purpose we can draw a line. So we can draw a line here until here before T1. You can see here is a change. If you look at this gradient, you see current is changing and the gradient of this line is negative. So in this case EMF, this one has to be positive. So let me first of all clear this line. So EMF will be positive. So in this short interval of time, EMF is positive for very short interval of time. So EMF is positive because gradient is negative. And after that, you can see gradient is 0. It means that EMF will be 0. So this is what you need to sketch. But we can also join them by dotted line, so it looks nicer. So this is how you can connect. So this is how you need to sketch the graph. This is how you need to sketch. And so let me show you a better one. But one thing you need to understand in this case is this gradient has to be shallower as compared with this one, because this gradient, you can see this is steeper, this is shallow. So this EMF has to be greater than this one. Now let me show you how you can sketch a proper graph, a beautiful one. So I have already drawn this one, so you can simply look at this. So this is how you need to sketch in your final answer. So this one you can use. I hope this one is clear to you, and this is the main concept. You need to understand this main concept. If this is clear to you in today's lesson, you will see most of the graph we will only answer based on this concept. Question 2 part B says two coils C and D are placed close to one another as shown in figure 5.2. The variation with time t of the current I in coil C is shown in figure 5.3. On figure 5.4 shows the variation with time t of the EMF induced in coil D for time t is equal to 0 to time t is equal to t5. And this question is very similar to the last one. In the last part we have discussed that EMF is equal to negative d5 by dt, or you can say minus d5 by dt, and EMF is also equal to negative. There will be some constant di by dt, or simply we can say negative gradient of IT graph, negative gradient of IT graph represents EMF, So this is the main concept. Now simply we need to look at the gradient of this graph and we need to sketch the EMF for coil D. If you look at this part, gradient is equal to 0. It means EMF until T1 it has to be 0. So EMF has to be 0 until T1. And after that, gradient is negative. This gradient is negative and this gradient is positive. So one thing we need to understand, this gradient is shallow. Very important point. You have to compare the next part as well. This is shallow, this gradient, and this gradient, this is steeper. This one is steeper. This gradient is negative and this gradient is positive. So here EMF has to be positive and here EMF has to be negative. Now let's try to sketch the graph. In the first part, until t1, gradient is equal to 0, so it simply means that EMF is equal to 0. So simply we can draw this line here. And in the second part, gradient is negative, so EMF has to be positive, so EMF will be positive. So we can see this is about 6 lines. So about 6 lines. So here until this, gradient is positive, and after that gradient is 0 because gradient in this part is equal to 0. So simply we can draw the line from here. So gradient is equal to 0. So until here gradient is equal to 0. Gradient is 0. This is until t3. So until here gradient is equal to 0, and after that gradient is positive, so EMF has to be negative. EMF has to be negative, and this is up to, we have t4. Yes, so it is up to t4 until here. So this is how you need to sketch. But one thing you need to consider is that this gradient is steeper, so EMF has to be greater. So EMF has to be greater, and this is from t3 to t4. Yes, so it has to be greater. So just approximate. Yes, you can show this one is greater. So this is how you can sketch. Now let me show you a proper graph, how you can sketch a better one. So this is how you can sketch. So few points you need to understand in this case are, one point is that if this one you show is positive, this one has to be negative, and this one has to be steeper than that. So this one has to be steeper. So you have to take care of these points. Part B says, on figure 10.3, sketch the variation with x of the EMF E induced in the coil for values of x from x is equal to 0 to x is equal to 6.0 centimeters. For this question, it is given to us coil is moving in a non-uniform magnetic field with constant velocity. With constant velocity. So this is given to us in the question, with constant velocity. So in this case, if you look at the given graph, we have flux on y-axis and we have x on x-axis. So as the coil is moving with a constant speed, it means that if the distance is the same, so until here we have 3 centimeters, also we have 3 centimeters here. So it means that if x is the same, speed is the same, so time taken also is the same. So now if you look at this gradient is shallow. So we can say this gradient is shallow because the time taken is the same, and this gradient is steeper, means there is a greater change in flux in the second part of this graph from 3 centimeters to 6 centimeters. So we need to sketch the graph between EMF and x. Again, EMF in this case, it has to be equal to minus d phi by dt. So this x is the same, so time taken also is the same. Time taken from 0 to 3 centimeters is the same as time taken from 3 to 6 centimeters. So simply the gradient of this graph, that is equal to EMF. So simply we can say negative gradient of phi x graph, because x is the same, speed is the same, so time taken is also the same. So simply we need to look at the gradient of this one, so gradient of this one is negative, so EMF has to be positive. So simply we can draw a line here up to 3 centimeters. So gradient has to be positive. Gradient is negative, EMF has to be positive, and gradient of this one is positive, so EMF has to be negative and steeper than this one, so we can draw here, so we can draw like this. So this is how you need to sketch, and if you wanna join them, you wanna connect them, we can also connect with this dotted line. So we can make it a little bit longer, but this is how you can sketch. So let me show you the proper one, the nicer one. So this is how you can sketch. This is proper graph, a nicer one. So this is how we can sketch. So you can say this is the gradient of phi x graph, because time taken from here to here and here and from 3 to 6 centimeters is the same. So you can say gradient of phi t graph. Question 9 part A says, state Faraday's law of electromagnetic induction. According to Faraday's law of electromagnetic induction, EMF is directly proportional to rate of change of magnetic flux linkage, d phi by dt, rate of change of magnetic flux linkage. And this is what you need to write down for the answer of this question. So simply you can say induced EMF is proportional to rate of change of magnetic flux linkage, and you will get 2 marks. Part B says, show that for a current of 2.8 amps in the solenoid, the magnetic flux linkage of the coil C is equal to this. So simply we need to calculate magnetic flux linkage of coil C. So we can say phi C. This has to be equal to NBA. NBA, number of turns on coil C, times the area of cross-sectional area of coil C times B, magnetic field. Number of turns of coil C we have, that is equal to 85, and the value of B here, so we have B here. B is pi times 10 to minus 3 times I. Current is here. Current is equal to 2.8 amps. Now we need to multiply with area. Area will be equal to pi times R square. So we can say A is equal to pi times R square. R is the radius. So the diameter of coil C, that is equal to 3.2, and the radius will be equal to 1.6 centimeters. Means 10 to minus 2 square of this one. Now if we solve this one, our final answer will be equal to 6.0 times 10 to minus 4 vapors. So this is what we need to show. Part C says the current I in the solenoid in B is reversed in 0.30 seconds. Calculate the mean EMF induced in coil C. First of all, let's try to understand how we can calculate mean EMF. Mean average EMF. This one will be equal to the total change in magnetic flux linkage. We can say N phi divided by delta T, or simply we can say this is equal to delta change in magnetic flux linkage, total change in magnetic flux linkage divided by delta T. And the change in magnetic flux linkage, we can also write down the final NABF minus NAB initial divided by delta T. T2 minus T1 you can write down, or simply you can say delta T. But in this case we need to understand direction of current is reverse. If direction of current is reverse, it means direction of magnetic field is also reversed. So we can say, let's say initial magnetic field is to the left, just for simplicity we can say to the left. So the final magnetic field, this one has to be to the right. Now one we have to take positive, so in this case we will take this one is positive, so this one has to be negative. Just to make things simpler, I'm just using this kind of convention. So it means that we can write down NA is common, so we can say BF, this is positive, negative, and we have negative B initial, and this is divided by delta T. So as BI is equal to BF in magnitude, they have the same magnitude, so we can say this is equal to B, this is equal to B. So it simply means that we have now NA, and this is 2 times of B, and this is divided by delta T. But we have already calculated magnetic flux linkage. We have calculated magnetic flux linkage. So magnetic flux linkage, in this case we can say this is magnetic flux linkage divided by delta T, and here we have 2 now. So this is 2 times the change in magnetic flux linkage in this given time. So simply we can write down now this is 2 times magnetic flux linkage in coil C we have already calculated, that was equal to 6.0 times 10 to minus 4, and divided by time. So the final answer will be equal to 4.0 millivolts. So the answer is 4.0. So beautiful question. You need to understand why do we multiply by 2, because in this case direction of current is changing, so it means direction of magnetic field is changing. So the change is double, means you have to multiply by 2. Changing magnetic flux linkage is double. Part D says the current I in the solenoid in B is now varied with time t as shown in figure 9.2. Use your answers to C to show on figure 9.3 the variation with time t of the EMF E induced in coil C. So we have I against time graph and we need to sketch EMF against time graph. And we have already discussed that EMF, this is proportional to minus di by dt, or simply we can say EMF represents negative gradient of IT graph, negative gradient of IT graph, or we can say EMF is equal to negative some constant di by dt, so simply EMF is proportional to negative gradient of IT graph. So we can say this is IT graph. So this is our main concept. But for this question we have to use our answer from C. In the C part we have seen for time delta t is equal to 0.3, we have seen that EMF induced, that was equal to 4.0 millivolts. So this point we have to use in our answer now. So first of all, if you look at the gradient here, this gradient is 0. It means EMF is equal to 0 in the first part. So we can say EMF here is equal to 0, and we can also draw the lines here to understand in a proper way. We can draw some lines. If I draw the line here, so this is here, this line is here, so I can also read this one. So I can draw the line here, and we can draw the line from here, and we can draw the line here to read time axis. The purpose is to read time axis. Now as gradient here is equal to 0, it means EMF is equal to 0. So we can simply draw EMF is equal to 0 until this point. And then if you look at this time is equal to 0.3 seconds. So this time is equal to 0.3 seconds. And EMF induced in this case, in this time period, in time 0.3 seconds, EMF induced, that is equal to 4.0 millivolts. So we can label these axes. So we can say this is 2, this one is 4. So it means between this time period, EMF induced is equal to 4 millivolts. So this is 4 millivolts. So we can draw the line here. So this is 4 millivolts because gradient is negative. So EMF is positive. And in the next part, EMF is equal to 0 because gradient of this part is 0. So gradient of this part is 0. So the EMF is equal to 0. And gradient of this part is positive. So the EMF will be negative. And if you look at the time here, delta t, time taken, this is equal to 0.6 seconds. 0.6 seconds. But the change in current is the same. So it means EMF will be half. Change in current is the same, but time is double. So it means if this is double, EMF has to be half. So EMF has to be half. So in this case, we can draw half 2. So this one will be 2. So this is 4. So minus 2. This is minus 4. So 2 from here. So this will be 2. You can draw horizontal line here. And in the last part, gradient is 0. So it means EMF will be equal to 0. So this is how you need to sketch the graph. I hope this one is clear to you. I hope you have got the idea. You have got the main concept, how to answer graph questions from electromagnetic induction. Now let me show you a proper graph, a nicer one. So this is how you can sketch a proper graph. So this is how you can sketch a proper graph. So this is what you need to sketch for this question. If this video was helpful, please like and subscribe because your encouragement is very important. And also, if you have any questions, please leave your questions in comments and I will try to answer as soon as possible. See you in next video. Welcome to A-Level and AP Physics. In today's lesson, we will discuss all possible graph questions from electric field and capacitance. We will discuss these questions in detail so you can improve your conceptual understanding of electric field and capacitance. And also, you can have better understanding of graph questions from these two topics. In order to get maximum benefit from these videos, always pause the video, do question first of all by yourself, and then watch the video to improve your conceptual understanding of these questions. Let's study together, let's improve together. Question 6 says, a solid metal sphere of radius capital R is isolated in space. The sphere is positively charged so that the electric potential at its surface is Vs. The electric field at the surface is Es. For part A, on the axis of figure 6.1, show the variation of the electric potential with distance x from the center of the sphere for values of x from x is equal to 0 to x is equal to 3r. So this question is basically about potential and distance. And in order to sketch this graph, we need to understand the relationship between electric field and potential difference. Electric field is equal to minus dV by dr. It simply means that electric field is equal to negative gradient of VT graph, negative gradient of VT graph. If E is equal to 0, so let's say if E is equal to 0, so then from here simply you can see that if E is 0, it means that dV, this is also equal to 0. It simply means that no change in potential. No change in potential, or simply we can say delta V is equal to 0. No change in potential, or you can say potential remains constant if electric field is 0. For this question, it is given to us the sphere is positively charged and the radius of the sphere is given to us, that is equal to capital R. So this one is our sphere. And electric field inside a sphere, is equal to 0. So this is the point you need to understand. Electric field inside sphere is equal to 0. If electric field inside sphere is equal to 0, it also means that delta V is equal to 0, or simply we can say V is constant. So V remains constant inside the sphere. So electric field inside any metal sphere is 0. If metal sphere is solid or metal sphere is hollow, electric field inside metal sphere is 0, because charges will be equally distributed at the surface and they will cancel each other's electric field. So electric field inside metal sphere is 0. So if this point is clear to you, it simply means that potential inside the sphere will not change, and it is given to us that potential, the sphere is positively charged so that the electric potential at its surface is Vs. At the surface is Vs, so it means at this point it is given to us that electric potential is equal to Vs at this point, and inside electric field is 0, so it means that potential inside will not change. So inside potential is constant, so potential will not change. And now we need to understand how potential changes with distance. So potential is inversely proportional to R. It means that for R, value of potential is Vs, and if R is double, Vs has to be half, so this will be Vs by 2. And if R is triple, this has to be equal to Vs by 3. We can simply say this will be equal to 0.5 Vs, and this will be equal to 0.33 Vs. So these are the points we need to understand. If these points are clear to you, it simply means that at this point at 2r it has to be half, so it will be here. So this is value of Vs, and here it will be about 0.33, so it will be about here. Now simply we need to connect these points, and if we connect these points, so your shape of the graph will look like somewhat like this. We can improve a little bit here. So the shape of the graph has to look like this. So this is how you need to sketch the graph. Let me show you a better one. So this is a better one. You can sketch your graph like this. Let me clean this one. This is what you need to sketch for your exam. So this is how you can sketch. I hope this question is clear to you. A typical type of question: potential inside a metal sphere does not change, it remains constant, and in magnitude it is equal to the potential at the surface. So for this question it was given to us that potential at the surface is Vs, so inside it is also Vs. Part B says, on the axis of figure 6.2 show the variation of the electric field with distance x from the center of the sphere for values of x from x is equal to 0 to x is equal to 3r. Now simply we need to sketch graph between electric field and distance from center of sphere. We have already discussed that electric field inside any metal sphere is equal to 0. Electric field inside any metal sphere is equal to 0, whether it is hollow or solid sphere. So in this case electric field is equal to 0. So inside electric field has to be 0. So simply we can draw the line. So at the surface of the sphere electric field will be equal to Es. So electric field is equal to Es. Now we need to understand how electric field is linked with distance. So we can say E is equal to KQ over R square. So from here we can see that if R is equal to capital R, then electric field is equal to Es. And for R is equal to 2 times R, Es has to be divided by 4. Mean this will be equal to 0.25 Es. And for R is equal to 3R, the value of Es, electric field, Es divided by 3 square means 9, divided by 9, and this one has to be equal to 0.11 Es. From here you can see it is very clear to you that E is directly proportional to 1 over R square. So these two quantities, they are inversely proportional to each other. So when R is double, this will be 1/4, and when R is triple, this will be E by 9. So it means the graph will drop quickly as compared with V against distance graph, because V is equal to KQ over R, and V is inversely proportional to R, but this is inversely proportional to R square, so that graph has to drop quickly. So these points you need to understand. Now when the distance is equal to 2R, it has to be 0.25. So here we have this is equal to 2, so it has to be 0.25. So here we have 0.4, it is divided into 5 parts, so it will be around here somewhere, here this value. And for 3R it will be round about here. So these are the points you have to mark first of all, and after marking simply you need to connect them. So here we can simply connect this one, so you see it drops very quickly. So the shape of the graph will look like this. You can also use dots here, so these are the dots. So these are the dots. And so this is how you can sketch the graph. So let me show you the better one, a bit better one. So this is better one. If I clean this one, so this is how you need to sketch the graph. So we can also clear, this is what you need to sketch for this question. I hope this one is clear to you. Part 2 says 2 point charges are situated in a vacuum and separated by a distance capital R. The force between the charges is Fc. On figure 5.1, sketch a graph to show the variation of the force between the charges with separation x for values of x from x is equal to r to x is equal to 4r. So in this case, simply we are talking about two charges, 2-point charges. Let's say they are positively charged, 2-point charges, and the force between these two when they're at a distance capital R, force between these two is equal to Fc. Now we need to sketch the graph how this force is changing with distance. If we increase the distance between them, how the force will change. For that purpose, we need to understand how the force is linked with the distance between the centers of the charges. So this is divided by r square. So from here you can simply see F is inversely proportional to r square. It simply means that for r is equal to capital R, F will be equal to Fc. F is equal to Fc. And for r is equal to 2r, F will be equal to Fc divided by 4. Divided by 4 means this one will be equal to 0.25 Fc. 0.25 Fc. And for r is equal to 3r, F will be equal to Fc divided by 9 means 3 square, and this will be equal to 0.11 Fc. And for r is equal to 4r, F will be equal to Fc divided by 4 square means 16, and this one will be equal to 0.06 Fc. Now simply we have the values of force and we have distance, and we need to sketch. We have distance and we have also values of F. So first of all, when it is distance is r, for the value of the force is this, and when the distance is 2r, the value of force is 0.25. so here we have 0.2, so this will be 0.22, 0.24, and somewhere here halfway this will be 0.25. So here this will be 0.25. 3r, this one has to be equal to 0.11. so here we have 0.2, so it will be halfway. 1 2 3 4 5, round about here, and 4r we have 0.06. so 1 2 3 at this point. So first of all, you can label these points. So let me clean the extra points. Now simply you need to connect these points. Simply we have to connect by this curve, so let me redraw this one to sketch a better one. So this is how you can sketch. So this is how you need to sketch the curve. Let me show you a better one, a bit better one. So this is how you can sketch a proper one. So this is how you can sketch a proper one. If you like, you can also label these coordinates because these points are very important. So here we have, this is 2r, 0.25 Fc. You can also label these coordinates 3r, 0.11 Fc, and this is 4r, 0.06. so this is very good one. So you can also label these coordinates. So this is how you need to sketch. Very similar to the electric field graph, electric field and force graph. The shape is the same because they follow the same inverse square law. Question 4 part B says a positive point charge plus q is located at a fixed point x and an identical positive point charge is located at a fixed point y, as shown in figure 6.1. The charges are separated in a vacuum by a distance of 10.0 centimeters. Points A and B are on the line xy. Point A is at a distance of 2.5 centimeters from x and point B is at a distance of 2.5 centimeters from y. The electric field at point A is equal to this value. So this is the net electric field at point A. So this is the net, E net. So value of E net at this point is given, so we can say in this case E net is given to us. E net is equal to 4.1 times 10 to minus 5 volts per meter. We need to find the value of charge, means the value of charge Q. In order to calculate value of Q, first thing you need to understand, it is given to us that net electric field at point A is equal to this. So if you look at electric field due to plus Q, due to this plus Q, this electric field will be pointing this way. So this will be pointing this way. We can say this is electric field EX. And electric field due to discharge, it also will be pointing opposite. It will be pointing this way. So we can say this is EY. If you're not very clear about this one, why this is to the left, you can simply sketch the charge. If you look at this charge, this is our positive charge. On the right side of this one, electric field is to the right. On the left side of this one, electric field is to the left. And on the top, this is pointing upwards, and here it is pointing downwards. So if you look at the right side of this one, electric field is to the right. If you look at the left side of this one, electric field is to the left. So the net electric field simply is the vector sum of these two. This is a vector quantity. This is also vector quantity. So it simply means that E net, this electric field has to be greater because this is closer to this charge. So electric field has to be, in this case, to the right. And this one has to be equal to the vector sum of EX minus EY. Now we can simply plug in values. Electric field due to discharge at point A, we can say this is equal to KQ over R square, because E is equal to KQ over R square, minus electric field due to discharge located at Y, this is to the left, so this is KQ over R square. But K, we need to understand, K is important. You need to understand K is equal to 1 over 4 pi epsilon naught. So you can see in this case we can take K out, K we can take out. So this distance is Rx, this distance is Ry. So KQ we can take out. So we left with 1 over Rx square minus 1 over Ry square. We just need to plug in values of these two. And value for K we have, that is equal to 1 over 4 pi epsilon naught, and here we have Q. And the value of epsilon naught we have, we can plug in that value. And we have value of Rx, means the distance between X and point A, that is equal to 2.5 centimeters. 2.5 centimeters. So this is 2.5 times 10 to minus 2. Minus 2 square, minus we have 1 over distance of this point charge from A, that is equal to 7.5. 7.5 times 10 to minus 2 square of this. Now if we solve this one, we will get the final answer, because value of E net we have, E net is given, we can plug in its value, that is 4.1 times 10 to minus 5. So let me plug in value of E as well. So we can rewrite here. We have, this is 1 over 4 pi epsilon naught. This is equal to 8.85. You can find the value of this constant in given data. So this is 8.85 times 10 to minus 12. And here we have Q, pi is a constant, its value is also given. And now simply we need to plug in value. We can simplify this one. You can say this is 0.025 square minus we have 1 over 0.075 square. Now simply you need to solve this one for Q. So this is 4.1 times 10 to minus 5. If you solve this one for Q, you will get value of Q is equal to 3.2 times 10 to minus 18 coulombs. So this is the charge on single positive point charge. So this is how you need to answer this problem. Your concept has to be clear. So you need to look at the electric field at this point. So this given electric field is the net electric field at that point. Part 2 says on figure 6.2, sketch the variation of the electric field E with distance d from A to B along the line AB. But the value of electric field we have already calculated at point A. At point A, the value of electric field was equal to 4.1 times 10 to minus 5 volts per meter. Actually, this value is given to you in the question. Now we need to understand, if we move from A to B, so let me use two different color. At point A, electric field is due to charge at X, and electric field at A is due to charge at Y. So this electric field is EY and this electric field is EX. Now we need to understand, if we move from A to B, EX will decrease because the distance from Q is increasing, and EY, this one will increase. And when we reach at the midpoint mean at a distance of 2.5 centimeter from A, so let me write on here the midpoint, because distance between A and B is equal to 5 centimeters. So when we are at a distance of 2.5 centimeters, so two electric fields, so let me draw here two electric fields, they will be equal in magnitude. So EX will be equal to EY in magnitude but in opposite direction. So these two electric fields, they will be equal. So the net electric field will be equal to 0 at 2.5 centimeters. Mean this is the distance D. So in this case we have 2 points. One point we have when we started from this point, value of electric field we have, that is 4.1 times 10 to minus 5. So we can label this point. And electric field is 0 at 2.5. So we have 2 here. So this is 2.1, 2.2, 2.3, 2.4, 2.5. So here electric field has to be 0. And again at point B, electric field has to be equal to this magnitude, because it is at a distance of 2.5 centimeters from this and 7.5 centimeters from X. So at this point, value of electric field again, so we can redraw the arrows. So here EX will be this way, so this will be EX, and EY at this point will be stronger electric field, so this will be EY. But the net electric field at point B, E net at B, this will be equal to this magnitude, so it also will be equal to this magnitude. And so it means that electric field at this point, it has to be this, but it will be in the opposite direction, because this is to the right, we are taking by convention positive, so this one has to be negative because this is in the opposite direction. So if we have understanding of these points, now we can draw the electric field. Now simply we need to connect these points to sketch the graph. So we have 4.1 here, and we have 0 at 2.5 centimeters, then it increases to 4.1, but it is negative. So this is how you need to sketch. So these 3 points are very important. This one has to be 4.1, this has to be negative 4.1, and this point has to be 0. So if you have sketched like this, you will get 2 marks for this question. A typical type of question between two identical positive charges. For the last part of this question on figure 6.4, we need to show the variation with distance y of the electric potential at point P for values of y from y is equal to 0 to y is equal to capital D. First of all, we need to understand it is given to us that capital D is the distance between the centers of these two spheres. And these two spheres, they are positively charged. If a sphere is positively charged, it means that its potential is also positive. So the potential of this one is positive. As this one is also positively charged, so its potential is also positive. Its potential is also positive at any point. So potential will not be negative. So potential is a scalar quantity. So we also need to understand potential is a scalar quantity. So now if you need to find the potential at any point, simply we need to add these two potential together and we can find the value of net potential. And also we need to understand electric field inside any metal sphere is equal to 0. So it means that potential inside the sphere, it will not change. So we will have maximum value of potential at this point. We can say this will be Vs. Let's say maximum Vs maximum, and we will have maximum value of the potential at this point as well. So this point also we will have Vmax. So let me rewrite this one. So this is also maximum value of potential, but potential inside this sphere will not change. So this is also Vmax. Now another point we need to understand, so we can label this. So this is one point you need to understand, this is the second concept you need to understand, this one is the third one, and this is the fourth one. And the fifth point we need to understand, at the center between these two spheres, electric field has to be 0 because they are positively charged sphere. So at the center of these two spheres, net electric field will be 0. So E net will be 0 at the center. If E net is equal to 0, so we need to understand E is equal to minus dV by dr. So it simply means that if E is equal to 0, it means that gradient of V against R graph has to be 0 at that point. Gradient has to be 0. It simply means that the gradient halfway between these two spheres of V against R graph has to be 0. So here we have a sphere, so we can draw these two small spheres. So we can draw one sphere here, and other sphere we have the center of the sphere is here. So we can draw this sphere here. So we have these two spheres. So the value of the potential at this point, so value of potential at this point will be maximum. So let me use different color. Value of potential at the surface, this one will be maximum, and value of potential at this surface also have to be maximum, same magnitude, so it will be here. So it also has to be maximum, and halfway it has to be 0. So halfway means that here this is the halfway. So let's say at this point potential will not be 0, but the gradient has to be 0. So we can draw this line here. Potential inside has to be constant inside metal sphere. Potential inside this one also has to be constant. And as the distance will increase from the sphere, potential has to decrease. So the potential will decrease. At this point it will be minimum, and then again it will increase. So this is how you need to sketch. So this is called the null point, means electric field is 0 at this point. Electric field is equal to 0. So this is how you need to sketch. If your concept is clear, you understand these knowledge points, sketching these graphs is not difficult at all. So one point you can remember, for two positively charged spheres, potential is never 0. Potential only can be 0 if one is positively charged and another is negatively charged. And if two spheres are negatively charged, potential will never be positive. Potential will never be positive. So if these points are clear, then it means you have good understanding of electric field. Welcome to A-Level and AP Physics. In today's lesson, we will discuss all possible graph questions from alternating current topic. And we will discuss these questions in detail so you can improve your conceptual understanding of this topic, and also you can have better understanding of graph questions. Let's study together. Let's improve together. Question 1 says an ideal transformer has 5000 turns on its primary coil. It is to be used to convert a main supply of 230 volts RMS to an alternating voltage having a peak value of 9.0 volts. For part A, we need to calculate the number of turns on the secondary coil. So we can simply sketch a transformer here, the basic structure, so you can get better idea. So we have primary coil, so this is the primary coil, and this is connected with alternating power supply. Transformer only work with alternating power supply. So it has primary voltage VP, and it has number of turns on the primary coil, we can say NP. And here we have the secondary coil. So this one is the secondary coil. We can also connect voltmeter here. So in this case we can connect voltmeter. So let's say we connect our voltmeter here. So this is over voltmeter, and reading on this voltmeter we can say this is Vs, and the number of turns on the secondary coil we have Ns. This is what we need to find out. Primary voltage is given to us, but primary voltage, this is RMS value. It is given to us, this is 230 volts, that this one is RMS. We can say this is RMS. And Vs is given to us, this is the peak value. So we can say this one is the peak value, and this is equal to 9 volts. And number of turns on the primary coil we have, that is equal to 5000 turns, number of turns. We need to find out Ns in this case. So for this purpose we need to understand the ratio between Vp over Np. This is transformer equation. This is equal to Vs over Ns. Now we need to find out in this case Ns. So Ns simply will be equal to Vs times Np divided by Vp. Now here problem is that this value is the RMS value and this is the peak value. So you cannot use two different values. You have to convert this one into RMS. Both of them has to be in RMS, or both of them has to be in peak value. Means both of them, they should have peak values or they should have RMS values. But in this case we will convert into RMS values. So we have V peak, so we can convert this one into VRMS. So simply we need to divide this one by root of 2. So this is the RMS value. Now we can plug in values. Vs, we have 9, this is divided by root of 2, and we have Np, that is equal to 5000, and we need to divide this one by Vp, that is already RMS value 230. Now if we solve this one, our final answer will be equal to 138. So these are the number of turns on the secondary coil. So the key concept is that you have to use both values, RMS values or peak values. Part B says the output from the transformer is to be full wave rectified. Figure 4.1 shows part of the rectifier circuit. On figure 4.1 we need to draw the diode symbols to complete the diagram of the rectifier such that terminal A of the resistor is positive with respect to terminal B. Means this terminal has to be positive, so current has to enter from this side. Positive means that current has to enter from this side, and negative means that current will be leaving from this side. Now we need to draw symbols of diodes to make a rectifier circuit, or simply we can say bridge rectifier for full wave rectification. This side is positive, this terminal is positive, and it is connected with this end of this diamond shape. So this has to converge. Diodes have to converge at this point, and from this point diodes have to diverge. Diverge simply means that the diodes have to be like this. Diverge. Converge means they have to be like this at that point. So here they have to diverge. So simply we can draw the symbol here, a symbol of diode. So this is typical symbol we use for diode. and here they have to diverge. So this is representing they have to diverge, and here they have to converge to this point. So we can draw these diode symbols like this, converge, and here again they have to converge to this point because this point end is connected with positive terminal of the resistor, converge. So this is how you need to draw, but we can also check is it correct or not. Let's try to use a different color. When this side of power supply become positive, this side become positive, so current in this case will flow like this. Current will go like this. At this point, current has two ways to go, down or this way, but current will not go this way because this is in reverse biased. So this is in reverse biased, so current will not go this way, but this is in forward bias, so current will flow this way. So we can say this is in forward bias, so you need to understand these terms as well. And so current will flow like this, but current cannot go this way because this is in reverse bias, so current will go this way and current will enter from this end. So this is positive terminal of resistor. Current will flow through this one. Then when current reach at this point, current has two ways to go. It can go this way or it can go this way, but current cannot go this way because this is at high potential. This is connected with positive, so the current will go towards low potential, so it will go this way. So this is how current will flow when the upper side of power supply is positive. After half cycle, this side will be positive. So let's use different color and see whether this is right or not. So we can use pink color now. So when this side become positive, this side positive, here current will flow like this. So let me use a better one, orange one, so that will be easy to see because pink is not that much clear. So we will be using orange one here, orange. So when this side is positive, current will flow like this, and when current is at this junction, it has two ways to go. It can go this way or it can go this way, but current will not go this way because this is in reverse bias, so current will not go this way. Current will flow through this diode, and again current will not go this way because this is in reverse bias for orange one, so current will enter from this side. So again you can see it is entering, so this is positive terminal. Then current will pass through this one, and when current reach this junction, current has two ways to go. One, it can cross this one, but this point, this is at high potential as compared with this one, so this is at low. So current does not flow from low to high, it flow from high to low. So current will flow this way and will pass through this diode. Again current will not go this way because this is at a higher potential, so current simply will flow like this. And so it means that our diagram is correct. This is correct diagram. If we go to the second part, we need to draw the symbol for a capacitor connected to provide smoothing of the potential difference across the resistor capital R, across this one. So for this purpose you need to understand, when you connect capacitor for smoothing, it has to be connected in parallel with the component. In this case component is resistor, so we have to connect this one in parallel with this resistor. So this is how you need to draw this diagram. I have explained you this one in detail. Now simply let me show you the answer, what you need to do for the answer of this question. So this is how you need to draw the answer for this question. I mean, these symbols you have to draw. This is how you need to draw, and I hope this one is clear to you. And this question is a typical type of question. Once it is clear to you, then it's a fun to play with full wave rectifier circuits. Part C says figure 4.2 shows the variation with time t of the smoothed potential difference V across the resistor capital R. For part C1, we need to state the interval of time during which capacitor is being charged from the transformer. So we need to understand, when capacitor is charging, it means the smoothed potential difference will increase. So simply we can say smoothed PD increases when capacitor charges. So this is the point you need to understand, capacitor charges. Now if you look at this interval of time from here to here, potential is increasing, so it means capacitor is charging here. So we can say this region is representing charging. And if you look at the next one, potential is decreasing, so this potential is decreasing. So this region, this is discharging, so this is discharging. So we can say charging, this is discharging, this is charging, this is discharging, this is charging, and this is discharging, and this part is also discharging. D for discharging. So we can write down any time interval. We can write down t1 to t2. We can write down there is no any other interval because this time is not given to us. So simply we can write down in this case from t1 to t2. So this is how you need to answer part 1. For the second part, it is given to us the resistance of the resistor capital R is doubled. On figure 4.2, sketch the variation with time t of the potential difference V across the resistor. So we need to re-sketch if resistance is double. So we need to understand when the resistance is double, the tau, the time constant. So RC. So if resistance is double, capacitance of capacitor is the same. So the tau of the capacitor will increase. If tau of the capacitor increase, it means capacitor will discharge slowly. Capacitor discharges slowly. So capacitor discharges slowly. So this is the point we need to understand. Capacitor discharges slowly, but time period of AC is the same. Time period of AC is the same, only tau for capacitor increases. So in this case simply we can draw at this point capacitor will discharge, but it will discharge very slowly. So let me redraw this one so we can redraw. Capacitor will discharge very slowly, so it will discharge slowly. So here it will charge, then again it will discharge, and again it will charge, and again it will discharge, and again it will charge, and again discharge, and so on. So this is how you need to sketch. Part C says a capacitor is now connected between the terminals AB of the output. The capacitor reduces the variation in the output to 1.6 volts. For part C1 on figure 11.2, we need to sketch the variation with time t of the smoothed output voltage for time t is equal to t1 to time t is equal to t2. First of all, before connecting capacitor, the variation in PD across a resistor is equal to 5.6 volts. Actually, if we draw the line here, we can see this is equal to 5.6 volts. And after connecting capacitor, we can say delta V, the variation in PD. After connecting capacitor, this is only 1.6 volts. So it means that we can draw a line 1.6. So 1.6 means 5.6 minus 4. So we can draw one dotted line here. 5.6 delta V 1.6. It simply means that PD is changing between two values. It is changing between 5.6 volts and between 4.0 volts. So the maximum is this one and the minimum is 4. So maximum and this one is minimum PD across the resistor. Now we need to sketch the curve. So it will reduce when capacitor will be discharging. PD across resistor will decrease to this value. Then capacitor will charge. PD across resistor will increase. It will reach 5.6. Then again it will discharge to 4.0, and then again it will increase. Capacitor will be charging, and then capacitor will discharge, so PD will decrease to 4.0, and then it will increase because capacitor will be charging. It will reach maximum value 5.6, and then again it will discharge. Actually we just need to sketch until here from T1 to T2. So this is T2. T1 means from this point to this point. And so this is how we need to sketch. So we can clear this line, we don't need this one. This is how you need to sketch for the answer of this question. Let me show you the better one. So this is a better one, a proper one. This is how you can sketch. So let me clear this. So this is how you need to sketch. Now if you go to the second part, for the second part we need to suggest and explain the effect, if any, on the mean power dissipation in resistor capital R when the capacitor is connected between terminals AB. So the power dissipated, this is equal to V squared divided by R. So in this case, the first case, before we have the maximum value, we can calculate V average. V average, we have 5.6 minus 0 divided by 2. So this is the V average. V average, and after we have the V average, that is 5.6 plus 4.0 divided by 2 V average. So we can see after the mean PD across resistor, it has been increased. So this is the mean PD. If this value has increased, it means the power dissipated in the resistor, that one has been increased because resistance of the resistor is not changing. So simply we can say, as mean PD increases, as mean PD, we can write down this one in a proper way, as mean PD increases across the resistor. So this one is greater than this value. As mean PD across resistor across R increases, so mean power dissipated, we can say, so mean power dissipation greater, or we can say higher. So that's all what we need to write down for the answer of this question. This question has 2 marks. If you have mentioned these 2 points, you will get 2 marks. Question 11 says a bridge rectifier contains 4 ideal diodes A, B, C, and D as shown in figure 11.1. The output of the rectifier is connected to a load capital L of resistance 2.4 kilo ohms. On figure 11.1, mark with the letter capital P the positive terminal of the load. So we need to mark the positive terminal of the load, means of this resistor. Positive terminal is the side through which current is entering. That side is positive terminal, and that one we can find out by just looking at this arrangement of diodes. So you can see at this side the diodes, they converge. So I can say diodes converge. So this is C. And if we look at this point, from here diodes, they diverge. So we can say this is D. And the C is connected with the load at this terminal. So it means this terminal is positive and diverging side is connected with the load here. So this side has to be negative. So simply we have to mark positive and negative. You can even check with the current. So we will check once. Let's say when this is positive, half of the cycle. So how current will flow? Current will flow like this. At this point, current cannot go this way. So current will pass through this diode because this is in reverse bias. So current will enter from this side. So this is positive. We can also check when the lower side is positive. When this side is positive, current will flow from here. It will go this way. But at this point, current cannot go this way because this is in reverse bias. So current will pass through this diode and again will enter from this side. So this is positive terminal of this load resistor. So this is how you need to mark. I have explained you in detail, but if you have understood this point, so simply you need to look the side are the point at which diodes converge, and that side is connected with positive terminal. So this is positive, and the point at which diodes diverge, that one has to be connected with negative. So this is how you can draw. For this question, simply you need to mark this positive and negative, means positive terminal you can mark with letter P. So this is simply you need to write down. Part B says the variation with time t of the potential difference V across the input to the rectifier is shown in figure 11.2. 2. We need to calculate the root mean square value of current in the load, capital L in the load. So we need to calculate IRMS. So we can simplify down. Here is IRMS. IRMS has to be equal to VRMS divided by resistance of resistor. But in this case we can simply read the V peak. So here we have, this is V peak. We need to calculate VRMS. So we have to divide this one by root of 2, and we need to divide by resistance of resistor. V peak we have 6. This has to be divided by root of 2, and we need to divide by resistance of resistor. And resistance of resistor in the previous part was given, that was equal to 2.4 kilo ohms. So 2.4 kilo ohms. Now simply we need to solve this one. If we solve, we will get this is equal to 1.8 times 10 to minus 3 amps. So this is our final answer. Pretty straightforward question. Part C says the potential difference across the load capital L is to be smoothed using a capacitor. For part C1 on figure 11.1, we need to draw the symbol for a capacitor connected to produce smoothing. So we need to connect capacitor across load resistor, and that has to be connected in parallel with resistor. So here this is how you need to draw symbol for capacitor. It has to be in parallel with this load resistor. Very common question, so you have to understand where to draw symbol for capacitor. Capacitor has to be connected in parallel with load resistor. Second part says the minimum potential difference across the load capital L with the smoothing capacitor connected is 3.0 volts. On figure 11.2, sketch the variation with time t of the potential difference across the load capital L. But if you look at this given curve, this is not rectified. This is pure AC signal from the AC power supply. And also we need to understand the minimum PD across the load resistor is given, that is equal to 3.0 volts. So first of all we can draw the line here. So we have 2, 4, this is 2, so 3 is between them, 1, 2, so 3 is somewhere here. So we can draw the dotted line first of all. So this is the dotted line. As this is not rectified, so we can assume this is a rectified. So we can draw rectified curves, and also we can draw this for the peak value. For the peak value we can draw one from here. This is also for the peak value, so we can draw here. This will help us to draw the curve in a nicer way. Now we can assume this is rectified, so we can draw this dotted line. This is rectified, so this is rectified signal, dotted. This will help us to draw the curve. Now we can draw the curve. So you need to understand here power supply PD is decreasing, so the capacitor in this case will discharge. Capacitor will discharge up to 3.0 volts. Capacitor will discharge up to 3.0 volts, and then from here capacitor will charge up to this point, and then again capacitor will discharge here, and at this point capacitor will charge again, and then again capacitor will discharge to 3.0 volts, and then capacitor will again charge, and then capacitor will again discharge to 3.0 volts. So the last one we can draw again, the last one, because this is not good looking, so we can draw in a nicer way. So this will discharge to 3.0 volts, and again this will charge, and again discharge, like this. So this is how you need to draw. But in the exam what you need to draw is simply you need to draw this blue one. Rest of the things are just for your understanding. If I want to show you the curve you need to draw, this is the curve you have to draw, but the way you need to draw I have explained you in detail, and I also hope that this one is clear to you how to draw this one in a nicer way. a bit tricky question. Maybe most of the students, they will get confused with this one, how to draw on the AC signal, because most of the time in the exam they will ask you to draw on rectified signal. Question 10 says the rectified output of a sinusoidal signal generator is connected across a resistor capital R of resistance 1.5 kilo ohms as shown in figure 10.1. The variation with time t of the potential difference V across R is shown in figure 10.2. For part A, we need to state how the rectification shown in figure 10.2 may be achieved. So if you look at this rectification, first of all, we need to understand what kind of rectification is this one. This is half wave rectification, because half of the cycle there is no PD across resistor. So this is half wave rectification. So we can say this is half wave rectification. Half wave rectification, and half wave rectification simply can be achieved by using single diode in series with resistor. Single diode in series with resistor means simply if we can connect one diode here. So if we connect one diode here, we can achieve half wave rectification. Single diode in series with R. In series with R. So simply we can say we have to connect single diode in series, single diode in series with capital R. So we can say connect single diode in series with R. So if you write on this one, you will get 2 marks. Part B says a capacitor is now connected in parallel with the resistor capital R. The resulting variation with time t of the potential difference V across capital R is shown in figure 10.3. Part 1 says use figure 10.3 to determine the mean potential difference across the resistor capital R. So we can see this is the maximum value of PD. So maximum, we can say V max. Maximum value of PD across resistor, that is equal to 6.0 volts. And we can find the minimum value of PD from here, minimum. And this minimum value of PD, this is 4.8. So we can write down V min. This is equal to 4.8 volts. And we need to find out the V mean value of PD, V mean. So this will be equal to 6.0 plus 4.8 divided by 2. So this is 10.4 divided by 2. So we will get 5.4 volts. So this is how we need to answer this question. For the next question, we need to calculate the mean current in the resistor and I mean in the resistor. So I mean, this is equal to V mean divided by resistance of resistor. V mean we have that is equal to 5.4, and resistance of resistor we have that is equal to 1.5 kilo ohms, means 1.5 times 10 to 3. And if we solve this one, we will get, in this case, this is equal to 3.6 times 10 to minus 3 amps. So this is the value of mean current. And if you go to the third part, the time in each cycle during which the capacitor discharges. So if you look at this given figure, from here we can see that in this part capacitor is discharging, mean here capacitor is discharging. Capacitor is discharging between these 2 points. Here capacitor is discharging, and simply we need to write down this time, and also we can write down this time is the same. Capacitor discharging, so we can draw another line. You can also take this time. Capacitor is also discharging between this one. So here capacitor is discharging. You can say discharge, and here also discharge in this interval of time. And this interval is easy to find because this is 0 and this is 0.027. So simply you need to write down this is 0.027 second. So capacitor is discharging for 0.027 seconds. Part 2 says using your answers in one calculate the charge passing through the resistor during one discharge of the capacitor. So we need to calculate value of Q. Q is equal to I times T. We have already calculated mean value of current, so we have to use the mean value of current and time of discharge, time taken to discharge. So we can say I T discharge. I we have calculated in the last part, that was equal to 3.6 times 10 to minus 3 amps, and value of time interval we have also calculated, that was equal to 0.027. Now simply we need to multiply and we can find value of Q. That will be equal to 9.72 times 10 to minus 5 coulomb. So this is our final answer, 9.72 times 10 to minus 5 coulomb. So this is how we can calculate. For the second part, we need to calculate the capacitance of the capacitor, and capacitance of the capacitor is equal to delta Q, means the amount of charge passing through the capacitor, divided by the change in voltage. Delta Q we have just calculated, that is equal to 9.72 times 10 to minus 5, and the change in potential across this capacitor, that is 6.0, means here we have 6 and here we have 4.8, minus 4.8 volts. And if we solve this one, our final answer will be equal to 8.1 times 10 to minus 5 farads. So this is how we can calculate 8.1 times 10 to minus 5. Part C says a second capacitor is now connected in parallel with the resistor capital R and the first capacitor. On figure 10.3, we need to draw a line to show the variation with time t of the potential difference V across the resistor. So in this case, we have connected an other capacitor in parallel with the first capacitor. So when two capacitors are connected in parallel, capacitance increases. So simply now we need to understand what is the effect of increase in capacitance on time constant of capacitor. So if capacitance increase, so time constant has to increase because R is constant. If tau increases, it means capacitor discharges slowly. So we can simply write down capacitor discharges slowly. And now if this point is clear to you, now simply we need to sketch a line, a curve on the previous curve. So let me show you how you can sketch in a nicer way. So this is how you can sketch. So you can see in this case, ripple, the variation in PD across resistor has been decreased. So now the ripple is only this much. So this is the ripple. And the previous ripple, let's use a different color. Ripple previously it was this big. Now the ripple has been decreased, means the variation in PD across resistor has been decreased by connecting another capacitor in parallel. If we connect in series, then C will decrease. C will decrease, time constant will decrease, so ripple will increase. Very important one, how capacitor is connected. If capacitor is connected in parallel, it means tau increase, ripple will decrease. So let me write down here, this point is very important. If two capacitors are connected in parallel, so the ripple decreases, variation in PD decreases, this will decrease. If in series, ripple, the variation in PD, this will increase. So next time they can ask you about this one. And that's all for today's video. We have discussed some beautiful questions on AC and rectification, and if you go through past papers and you take all the questions about graph from this topic, you will see only these different types of graphs. So it simply means that we have covered all possible graphs about AC in today's lesson. If this video was helpful, please like and subscribe, because your encouragement is very important to make more videos. More encouragement, more videos. See you next video. Welcome to A-Level and AP Physics. In today's lesson, we will discuss all possible graph questions from gravitational field and simple harmonic motion. We will discuss these questions in detail as always we do, so you can improve your conceptual understanding of gravitational field and simple harmonic motion. And also you can have better understanding of graph questions from these two topics. Let's study together, let's improve together. Question 2, part A says, state the relationship between gravitational potential and gravitational field. This question is very common in past papers, and also this concept is very important to answer past paper questions from this topic. Let's try to understand how these two quantities are linked with each other. We can simply say G as a function of R, this is equal to negative dV by dr. dV by dr, this is simply gradient of, this is representing gradient of V against R graph, mean potential against distance graph from the center of massive object, gradient of VR, and this is the negative, so we can say, so G is equal to negative gradient of VR graph. And the meaning of negative sign is very important. What this negative sign is telling us, negative sign means that G is, or you can say G points towards decreasing potential, very important one, points towards decreasing potential. Which way potential is decreasing? G is directed towards that direction. So you can also simply understand with a very basic example. This is, let's say this is a sphere, this is a massive object. If you look at this point, if we go up, potential will increase. So I will say if we go up, potential will increase. But if we go, potential will increase. But if we go down, potential will decrease. So it means that G is, direction of G is in direction of decreasing potential. A beautiful point. Later you will see the importance of this with the help of graphs. Now let me show you how you can write down the answer for this question. For the answer of this question, simply you can say gravitational field equals negative gravitational potential gradient. Means you take the gradient of V against R graph and add negative to that. That is the value of G. Part B says a moon of mass capital M and radius capital R orbits a planet of mass 3m and radius 2r. At a particular time, the distance between the centers is capital D, as shown in figure 2.1. Point P is a point along the line between the centers of the planet and the moon, at a variable distance x from the center of the planet. The variation with x of the gravitational potential phi at point P for points between the planet and the moon is shown in figure 2.2. Simply graph between potential against distance is given to us. Part B1 says explain why phi is negative throughout the entire range from x is equal to 2r to x is equal to d minus capital R. Means from this point to this point, why potential is always negative. This question is very common question. They will ask you this question in many different ways. So you need to clear your concept how to answer this type of problems. Let's try to understand this one with one very simple example. We can imagine that we have one capital mass M. This is mass capital M. And now you can also imagine that we have one test mass. So let's say this is one small test mass. So this is test mass. And we can also assume at infinity. So here we can define infinity. At infinity you need to understand that we take potential is equal to 0. Gravitational potential at infinity is 0, and electrical potential also we assume at infinity is equal to 0. Because in physics potential difference is defined but potential is not defined. That's the reason we assume a reference point. So we always assume this is as our reference point, mean infinity. So if potential is 0 at infinity, it also means that at infinity GPE is also 0. Now imagine that if we move this mass up, is the separation between these two objects, is it increasing or is it decreasing? So you need to understand in terms of separation. As separation is increasing between these two masses, I hope you will say GPE is also increasing. Now assume the same test mass at this point. Now this is moving down. Now is the separation between these two objects, is it increasing or is it decreasing? I hope you will say separation is decreasing. So if separation is decreasing between these two massive objects, it means GPE is decreasing. Now at infinity we have GPE that is equal to 0. That as object is moving down, GPE is decreasing. As GPE is decreasing from 0, it means this one has to be negative GPE anywhere from this point to this point. GPE has to be negative. So that's the reason GPE is always negative. GPE is always negative because at infinity we assume potential is 0 or we assume GPE is 0. So that's the reason potential is always negative other than infinity. For gravitational field we are talking about, but for electric field potential can be positive, it also can be negative. We will go to that point later. Now we need to understand why this GPE is decreasing, because in this case work is done by force, work is done by gravity. So work is done by gravity, or simply you can say gravity is an attractive force. Work is done by gravity, that's the reason GPE is negative, or you can say GPE is decreasing. So simply we can say in this case as test mass getting closer to the massive object, or we can say separation is decreasing from infinity, it means GPE decreases. So these points you have to write down in your answer. So let me show you the answer, how you can write down your final answer. So in your final answer you can mention these 3 points. One point you can say potential is 0 at infinity. We have already discussed that potential at infinity is 0. Second, you can say gravitational force is attractive, or you can say when work is done by gravity GPE decreases. So we can say this is the second point. The third point we can say as separation is decreasing. So this can be the third point. As separation is decreasing, GPE is decreasing. So these 3 points you have to mention in your answer. And this question is very common, so you have to master this concept. Part 2 says one of the features of figure 2.2 is that phi is negative throughout. Describe 2 other features of figure 2.2. So this is our figure 2.2. If you look at this figure 2.2, we can simply compare the potential at the surface. We can compare potential at this point and we can compare potential at this point. Potential here, this is more negative as compared with this potential. So simply we can say this potential here, phi is smaller. So the potential at surface of planet is smaller. If you look at the gradient at this point, and we look at gradient at this point, this gradient is also shallower. So the gradient at the surface of planet is shallow, and this one is steeper. So this one is steeper. And gradient we have already discussed that G is equal to negative dV by dr. So if gradient is greater, it simply means that G is higher. This negative telling us direction. So don't get confused with this negative. Negative telling us direction of G. So this is shallow and this is steeper. It means G at the surface of moon. So G at surface of moon, this one is greater than G at surface of planet. And the potential at the surface of the moon, we are just talking about the surface. As this one is more negative, potential scalar quantity, potential is scalar, G is vector. So this negative is giving us direction of G. As this is more negative, it means G at the moon, this one is greater than means the phi at the surface of moon, this is greater than phi at the surface of planet, because potential at the surface of the planet is more negative, it means it is smaller. And also we can say about the point of maximum potential. So at this point potential is maximum, and this point is closer to the moon because this side is representing moon. On this side we have moon, on this side we have planet. So these are the points you need to understand. So we can talk about potential at the surface of planet, we can talk about potential at the surface of moon, we can talk about value of G at the surface of moon, we can talk about value of G at the surface of planet, and we can compare them. Potential is a scalar, as potential is more negative at the surface of the planet, it means this potential at the surface of the planet is smaller than the potential at the surface of the moon. As this gradient is less steep and this gradient is more steeper, it means that the value of G at the surface of the moon is greater than value of G at surface of planet, and the point of maximum potential is closer to the moon. So you can mention these points. We have discussed 3 points. We need to write down only 2 points. Let me show you the answer, how you can write down this one in a proper way. And so simply one point you can say, potential at surface of planet is smaller than at surface of moon, as we have discussed here. So this one point you can write down. Second, you can say potential gradient. Potential gradient means you're talking about G. At surface of planet is smaller than at surface of moon, as we have discussed this point here. And the point of maximum potential is closer to the moon. So this is point of maximum potential, we can say phi max. And magnitude of potential you can also say varies inversely with distance from center near the sphere. Near the surface it is inversely proportional to distance. So these points you can mention, very important points, you need to understand these points. Third part says, on figure 2.3 sketch the variation with x of the gravitational field G at point P between x is equal to 2r and x is equal to d minus r. So for this question simply we have to sketch graph between G and distance, but we have graph between potential and distance. So simply we need to understand how potential and gradient, potential and G, they are linked with each other, means the relationship between these two quantities. We have already discussed that G is equal to negative dV by dr, mean this is negative potential gradient. Mean if we have the graph between V and R, simply we need to find the gradient. So the gradient of VR, this is equal to negative G, or we can say negative gradient of VR, this is equal to G. That's all. So simply we have to look at gradient of potential against distance graph. If you look at this gradient, this one is positive. So gradient is positive. So for the gradient I will be using letter small m. Gradient is positive. So G has to be negative. And if you look at gradient at this point, gradient is equal to 0 because this is horizontal, so G has to be 0. If you look at this part, gradient is negative, so G in this part has to be positive. Mean after that G is negative, before this one G is negative, and after this one G is positive. And we need to compare the gradient at this point, and we need to compare gradient at this point. Now this gradient is shallow, we have already discussed this point. So this is shallow and gradient at this point is steeper. It means G at this point is greater as compared with G at this point. So in this case simply we can mark the point. So this point should be at low value of G, and this has to be at higher value of G. So if we have these things in our mind, we can mark the points. We can mark this point first of all, then we can mark this point, then we can mark this point, and then we can sketch the graph. So let me show you how you can sketch a proper graph. And so this is how you can sketch a proper graph. So this point is very important. It has to be at lower value of g, and here we should have higher value of g. And the point where gradient is 0, this one has to be equal to 0. So this is how you need to sketch very important graph from this topic. Part B says, apart from the quantities in A, describe what may be deduced from figure 4.2 about the motion of the trolley between time t is equal to 0 and t is equal to 24 seconds. No calculations are required. So if you look at this given system, in this case, L is measured from this spot X. So if the trolley is moving to the right, L will increase. And if trolley is moving to the left, L will decrease. If you look at this given graph, we can see the initial position of the trolley is 25, mean L is equal to 25. Maximum value of L is 25 and minimum value of L is given, that is equal to 15. We have L on y-axis and we have t on x-axis. It means it is oscillating between two values of L, 25 and 15. As the initial value of L is 25, it means that initially we pull the trolley to the right. So we can say initially trolley is pulled to the right, so this one point we can write down, pulled to the right. So this is one thing we can deduce from here. And the second thing we can find out is, if we look at time period of this one, its time period is equal to 4 seconds. So we can say time period t is equal to 4.0 seconds. And also if we look at this motion, first part of the motion, this motion is undamped and this one is damped. So this is undamped. So we can also deduce from here. So this is undamped motion and this one is damped. This is damped. But this damping is light. So this is light damping because this is amplitude is decreasing exponentially and gradually. So we can say light damping. So we can say light damping. So third point we can say initial motion is undamped, means this part. Initial motion is undamped. And the fourth point we can say it's light damping. We can say after some time, after 12 seconds, we can say after 12 seconds, its damping is light damping. Its damping is light damping, or simply we can say after 12 seconds light damping. So in a simple language you can say after 12 seconds light damping. So it's easy way to write on. So we can say after 12 seconds light damping, means the motion is damped. And also we can conclude from here, at this point when t is equal to 0, it is at rest. But if you look at this point here, and if you look at this point, this is at 1 second, this is at 3 seconds. So this is 1 second, this is 3 seconds. We can say this is the equilibrium position. So this is very important one. So where is the equilibrium position? It is at 20 centimeters when L is equal to 20 centimeter. Equilibrium position is at 20, and at equilibrium position speed is maximum. So we can also say maximum speed. We can write down in a simpler way. We can say Vmax. So we can write down in a simpler way. We can say Vmax at 1 second, 3 seconds, and so on. And also we can say in this case stationary at, we can say stationary at, if we look at this point, for example, you can say 2 seconds. It is also at rest at this point. We can say 4 seconds, 4/5, and it is also at rest at this point. This is also here, so 6 seconds and so on. Simply we can say so on. So you can see these points you can deduce from the given graph, and it's a very important skill how to read the graph. So you need to understand how to read the graph. So this is how you can read the graph. Now let me show you the proper answer in written in a proper language. So this is how you can write down a proper answer. This is what you need to write down for the answer of this question. So at least 3 points you have to write down. 3 points. So but we have talked about 5 different points. If you mention 3 points, you will get 3 marks. Part C says on figure 4.3, sketch the variation with capital L of the velocity v of the trolley for its first complete oscillation. Before we answer this question, one thing we need to understand is that for this question it is given to us that V max of the trolley is 7.9 centimeters per second. This has been calculated in the previous part of the question, because in today's class our main goal is graph, so that's the reason we haven't done that part of the question. But V max is given to us, that is equal to 7.9 centimeters per second. So we have to sketch the graph between V and X, and V and X, they are linked with each other. V is equal to plus minus omega into a square minus x square, and X is the displacement, A is the amplitude. So this is the equation that connect V and X, and how V is changing with displacement from equilibrium. When X is 0, V will be maximum. So we can also write down V max, it is when X is equal to 0. So we will get omega times A, and this is at X is equal to 0, means when it is at equilibrium. So these points we need to understand. Now when we have this type of questions, we have to figure out first of all where is the equilibrium. In this case the equilibrium is at 20, means L is equal to 20. So we can draw the line here. So this is the equilibrium. So first thing we can write on here, equilibrium is at 20. So equilibrium is at this point, and it is oscillating between 25 and 15. So it is oscillating between these points. And also we have the maximum value of V, that is equal to 7.9. So here we have 10, 5, so it means each small square, this is equal to 0.5. So it means here we have 5, so here we will have 6, here we will have 7, and here we have 7.5, and here we have about 7.9. And we can also mark here, so we have 5, here we will have 6, here we will have 7, and here we will have 7.9. So now simply we need to connect this one. So the shape can be circle, shape can be ellipse. It depends on the given axis. On given axis, scale, it depends on the scale. Shape can be circle or it can be ellipse. So let me show you the final answer. So if you connect these points, so this will be the shape of the graph. So this will be the shape of the graph. So it's better to write down the coordinates. So when V is maximum, when X is equal to 0. So we have maximum V here, we have maximum V here. And when X is maximum, speed has to be 0. Means when X is equal to a square, speed will be 0. So this is point here, speed is 0, speed is 0. So this is how you need to sketch a typical type of graph. You need to be clear how to sketch this. Shape is depending on the scale, very important. It can be circle, it can be ellipse. Part B says the resistance of the resistor capital R is increased. The magnet is again displaced a vertical distance capital D and released. On figure 7.2, sketch the variation with time t of the displacement small d of the magnet. So in this case resistance has been increased, so simply we can write down EMF, this is equal to I times R, and from here we can write down I, this is equal to EMF divided by R, and this I is the I induced. EMF is the same because initial displacement is the same. As resistance has increased, it means I will decrease. If induced current decreases, it means magnet loses less energy. Means less mechanical energy of the magnet decreases. Magnet loses less energy. As less energy is lost, it means that less damping. So simply we can say less damping, less damping, less damping. Simply we can say less mechanical energy has been converted into electrical energy. So it means less damping. If less damping, it means that d new it has to be greater than d old, because amplitude of this magnet, or simply we can say displacement of the magnet, it will decrease less, because less mechanical energy of the magnet has been converted into electrical energy. As magnet is losing less energy, it means less damping. So the new displacement at any given time has to be greater than the initial displacement, or we can say the previous displacement, as shown in the curve. So now simply we need to sketch the curve, but time is the same. Time period does not change in this case. So this is how you need to sketch. So you can see at any given time, the red one, displacement is greater than the displacement of the previous curve. So displacement is greater. So this is how you need to sketch. This is how you need to sketch. Time period is the same, but only displacement at any given time is greater than before. Part C says the resistor capital R in figure 7.1 is replaced by a variable frequency signal generator of constant RMS output voltage. The angular frequency omega of the generator is gradually increased from 0.7 omega naught to 1.3 omega naught. Omega naught is the angular frequency calculated in A2. For part C1, on the axis of figure 7.3, sketch a graph to show the variation with omega of the amplitude A of the oscillation of the magnet. A beautiful question about resonance. First of all, it is given to us this resistor is now replaced by signal generator. So simply we can say here we have now signal generator. So this one is signal generator, variable frequency signal generator, variable. So I can mark this one here. So it's variable frequency signal generator, meaning the frequency we can change. Variable frequency signal generator. So we have variable frequency signal generator. So it will send alternate current, variable current to this coil, and this coil will produce its own variable magnetic field, and the frequency of the generator we can change. So it simply means that we can change the frequency of current, induced current, and also we can change the frequency of induced magnetic field. And this magnet, it has certain natural frequency. It is oscillating with a certain natural frequency. And when this become a magnet, at one instant they will repel each other. At another instant, these two magnets, they will attract each other, means there will be electromagnetic forces. And if we keep on changing the frequency at one certain frequency, when the frequency of the magnetic field induced in this coil matches with frequency of this oscillating magnet, means the natural frequency of this oscillating magnet, resonance will take place, and that resonance will take place at omega naught, means at this point it will take place. Resonance will take place at natural frequency of this magnet. So we can say here resonance will take place because driving frequency will be equal to the natural frequency of this harmonic oscillator. So resonance will take place, and when resonance takes place, amplitude of oscillations will be maximum, and if we increase more frequency, it will start to decrease. And so these points we need to understand. So it simply means that this is now driven oscillator by electromagnetic forces, means by interaction between two magnets, or simply we can say between two magnetic fields. And this is a typical type of graph. Let me show you how you can sketch. So this is how you need to sketch this one. This is the initial amplitude of magnet. As we increase the frequency of the variable signal generator, and its frequency is getting closer to the natural frequency of oscillating magnet, you can see amplitude is increasing. So here natural frequency of oscillating magnet is equal to the frequency of magnetic field induced in this coil, so resonance takes place at this point. If we increase more frequency, amplitude will not increase, amplitude will start decreasing. So this side has to be lower than, you see this amplitude is even lower than this one. So this is the initial amplitude of this oscillating magnet. So this point you need to understand. So this is how you need to sketch this curve. Let's try to understand a little bit more about this one. Here sometimes they will ask you to sketch curves like this. So this is when no damping. You can see amplitude is infinite, mean amplitude go on increasing if there are no resistive forces or if there is no damping. In this case, amplitude has certain value because this is not in a vacuum. There is air, so there are some resistive forces, so it has light damping. And then if we increase damping, you will see the time period, the frequency has shifted to the left. When frequency has been decreased, so with damping, time period increases. This one you no need to show in the previous part, the graph shape as we have sketched in the previous part, but for this type of graph you have to show that. And you can see even we increase the damping here, so this one has light damping and this one has medium damping. You see the frequency has decreased, it means time period has increased, time period of oscillation. And for heavy damping, you can see the natural frequency is here now, so the natural frequency decreases with damping. So this is very important point. So these points you need to understand. So this curve is very important one. So the frequency is decreasing. So let me draw the lines here. So you can see the frequencies here. Initial frequency, we have that one was here, and here you can see now. So these points you need to understand. So on these curves you have to show that time period is increasing with damping, but as we have sketched in the previous one, you no need to show that time period increase. We will assume time period does not change. Part B says, use your answers in A to plot on the axis of figure 3.3 the variation with displacement x of the acceleration A of the ball. So simply we have to sketch the graph between A and x. So we need to sketch a graph between these two quantities. So we need to figure out what is the relationship between these two quantities. A is equal to minus omega square x. Now if we compare this one with y is equal to mx, from here we can say m is equal to negative omega square. It means gradient is equal to negative omega square, or we can say omega square is equal to negative gradient of ax graph. So this is the point we need to understand. But from here we can also deduce that A is directly proportional to negative x. Very important point. It means A and x, they are directly proportional, but they have opposite signs. Means when this is positive, A has to be negative, and when this is negative, A has to be, when this is negative, A has to be positive. When this is positive, A has to be negative. Means when this is positive, this has to be negative, and when this is negative, this has to be positive. So the gradient in this case has to be negative, means the gradient of the line, it has to be negative. So let me show you how you can sketch the graph. Actually you no need to worry about the numbers, because these numbers we already have, we have calculated in the exam. These numbers will be given to you, but our main focus is on the graph, how to sketch the graph. So in the question it was given to us that when A is equal to x is equal to this one 1.7, value of A is equal to 5.2. So this has to be negative because this is positive, and when x is negative 1.7, A has to be positive 5.2. So it has to be a straight line, and the gradient of this one has to be equal to omega. Gradient has to be equal to negative omega square. So this is very important, and omega is constant, so gradient has to be constant. So we have discussed a lot of questions about simple harmonic motion, and also we have discussed one question about gravitational field. I hope if you have watched this video carefully, you have good understanding of these two topics. And if this video was helpful, please like and subscribe, because your encouragement is very important. See you in next video. And also, if you have any questions, please leave your questions in comments.